So far, we've been drawing Lewis structures as flat 2D shapes. We know that real molecules aren't actually shaped like that. So we need some sort of theory that's going to help us translate our two-dimensional Lewis structures into an actual 3D shape. And the simple of these is what's called VSEPR theory, where VSEPR stands for valence shell electron pair repulsion. VSEPR is a really simple model, though it works really well, that simply states that electron repulsion is what determines the overall shape of the molecule. Or more simply, electrons don't like each other. Like charges repel, and so all of my electrons are going to get as far away from each other as possible in the molecule. And that's going to tell me my lowest energy preferred geometry. So electrons come in what we call groups, where a group is either a lone pair or a bond, and whether it's a single, double, or triple bond, that still just counts as one group. And these electron groups are going to get as far away from each other as possible. So if we look at a molecule, all we really need to do is count how many electron groups are around the central atom, and then we can translate that into a basic shape. So we can see we have 5 basic shapes here according to the number of electron groups. So 2 electron groups here, that would be a linear molecule, and so the angle between those 2 electron groups there would be 180 degrees, which is as far away as they can possibly get from each other. 3 electron groups is going to be trigonal planar, and now that angle between the electron groups is 120 degrees on all 3 sides, because again, that's as far away as those electron groups can get from one another. The first 2 shapes are still somewhat flat if we look at the pictures, but this 4th shape, tetrahedral, is very much 3-dimensional, almost looks like a little period. And now that angle there is 109.5 degrees. 5 electron groups, this is probably the hardest one to pronounce, trigonal bipyramidal, and we can see it looks like 2 3-sided pyramids, one sort of stacked on top of the other. Last one, when you have 6 electron groups, is octahedral. So these are our 5 basic shapes, really simple. We just need to count the number of electron groups and we can get our shape. We do need to be careful of one other thing, however. Notice that lone pairs are an example of electron groups. However, we can't actually see electrons. They're much too small. So we can't see lone pairs when we look at a molecule. So it turns out we actually have 2 different types of geometries. We have what's called electron geometry, and we have molecular geometry. Electron geometry is the geometrical arrangement of the actual electron groups. So if we look at the simple example of water here, water has 4 electron groups. 2 lone pairs, and then 2 bonds. So this guy has 4 electron groups, but 2 of them are lone pairs. Since we can't actually see those lone pairs when we look at the molecule, it looks like this down here. It doesn't look like a tetrahedral, which is what it should look like with its 4 electron groups. So the molecular geometry is the shape we can actually see. So how do you determine each one? Well, really simple. The first thing you need to do is simply draw the Lewis structure. The second thing is you count how many electron groups you have, and that will tell you your overall shape according to this chart up here. Then what you do are count how many lone pairs you have, and then that will tell you the molecular geometry. So electron geometry is just based on how many electron groups you have, and the molecular geometry is based on how many lone pairs you have. So we have this nice little chart here to help us. So if we go back to our example of water, we said had 4 electron groups and 2 lone pairs. So we would come down and say, okay, 4 electron groups, that means its electron geometry is tetrahedral, but it had 2 lone pairs, which means its molecular geometry would be bent. Electron geometry tetrahedral, that's how it's arranged, that's how its electron groups are arranged. Molecular geometry bent, because that's how we actually see the molecule. Notice that if you have no lone pairs, which is this column right here, the electron geometry and the molecular geometry are the same. So when you have no lone pairs, life is really simple. They're the same thing. But as soon as you start having lone pairs, we get these different names in here. Sad news, you just have to memorize these. There's nothing else you can do. Let's look at a couple more examples. Look down here. Now, I've kind of cheated and gone ahead and drawn the Lewis structures for these. You'll need to draw them. So you would just be given this information over here. You have to first draw the Lewis structure and then work on the VSEPR. But let's just, for the example, go ahead and start looking at our Lewis structures. So first example, CH4. CH4 has 1, 2, 3, 4 bonds, so 4 electron groups, and it has 0 lone pairs. So 4 electron groups and 0 lone pairs. We'll go back up to my chart. 4 electron groups, its electron geometry is tetrahedral. 0 lone pairs, its molecular geometry is also tetrahedral. Really simple. All right, next example, we have CO2 here. CO2, it has 2 electron groups, because remember, those double bonds still count as just 1 electron group. Now, we just look at the central atom when we do the VSEPR theory. So the central atom has 0 lone pairs. I realize the oxygen atoms have them, but we're looking at the carbon, that central atom right there. So we have 2 electron groups and 0 lone pairs. So we go back up to my chart. 2 electron groups, electron geometry is linear. No lone pair, molecular geometry also linear. Really, really simple. All right, now let's try SO2. Pretty similar. SO2 has 1, 2, 3 electron groups. And one of these, the top one there, is a lone pair. 3 electron groups, 1 lone pair. So I'll go back up. 3 electron groups, my electron geometry is trigonal planar. 1 lone pair, my molecular geometry is bent. So electron geometry, trigonal planar, molecular geometry is bent. Now the last example, we have SF4 here. So here we're going to look at sulfur, and again, 1, 2, 3, 4, and this one actually has 5. Don't forget about that lone pair. So 5 electron groups, that's a G, and 1 lone pair. 5 electron groups, 1 lone pair, so we go back up. 5 electron groups. My electron geometry is trigonal bipyramidal. 1 lone pair, so my molecular geometry is seesaw. So again, you're not going to have this chart, you just need to memorize all these shapes, but the basic idea is always the same. Count your electron groups, get your electron geometry, count your lone pairs, get your molecular geometry. Now we'll do one more example here of a larger molecule. So previously we were doing molecules with just 1 central atom, but we can actually do this with a larger molecule that has multiple interior atoms. And by interior, I mean it's bonded to more than one thing. So my interior atoms here would be this guy, and this guy. Those are my 3 interior atoms. And we could do this process for all 3 of them. So I'll call these C1, C2, and O. C1, C2, and O. All right, if we look at C1, it has 4 electron groups. It has 0 lone pair. So its electron geometry is going to be tetrahedral. And its molecular geometry, because it has 0 lone pairs, is going to be the same thing. So that's going to be tetrahedral. So C1, electron geometry tetrahedral, molecular geometry tetrahedral. C2 here. C2 has 3 electron groups. Oops, that's an E. And again, 0 lone pairs. So 3 electron groups. The electron geometry is trigonal planar. And because it has 0 lone pairs, the molecular geometry is also trigonal planar. Very, very simple. Finally, we'll look at oxygen here. Oxygen here has 4 electron groups. So that means his electron geometry is going to be tetrahedral. But he has 2 lone pairs, 4 electron groups, but 2 lone pairs. His molecular geometry is going to be bent. I don't have to worry about any of the other atoms because they're exterior atoms. Only need to worry about those 3 interior atoms. But I'm going to do the same exact process that I did before.